Welcome, my dear learners, for this course on control engineering. In this final module, that is in module 5, we are discussing on board plot. We have started our discussion on problems on board plot. Let us continue our discussion. The problem number 2 states that a unity feedback control system has g of s into h of s is equal to k divided by s of s plus 4 into s plus 10. Draw the board plot and find the value of k for which the system is marginally stable. Note on the word marginally stable. For marginal stability, the phase crossover frequency must be equal to gain crossover frequency. That is the condition for marginal stability. Kindly make a note. Use this condition to find the value of k. Let us quickly solve this problem. If I move for solution, you should make a note that for marginal stability, gain crossover frequency must be equal to phase crossover frequency. Keep this in mind. Omega gc must be equal to omega pc, phase crossover frequency. Now in step 1, as usual, write the given function in its standard time constant form. Obtain the standard time constant form. If I go for standard time constant form, the given equation is of the form g of s into h of s is equal to k divided by s of s plus 4 into s plus 10. Correct? Now the standard, if you carefully observe, we have the constant k. Its numerical value is not known. We should find out how much is k, and then we have one pole at origin and two simple poles. Now the standard form for simple poles is of the form 1 plus ts. So therefore I should take 4 common. Here I should take 10 common. Let us do that. If I do that, what I am going to get? I will get k divided by s into, I should take 4 common. It will become 1 plus s by 4. Here I should take 10 common. It will become 1 plus s by 10. 1 plus s by 10. Now k by 40. K by 40, what I am going to get? K divided by 40 is what I am going to get, right? 4 into 10 should be sent into numerator. It will become k by 40. Let me call k by 40 as k dash. K dash divided by s of 1 plus s by 4. How much is 1 by s plus 4? That is 1 by 4, which is nothing but 0.25 s. 0.25 s, and we have 1 by 10. That is 0.1 s. 1 plus 0.1 s. So we obtained the time constant form where k dash, what is the value of k dash? K dash is equal to actual k divided by 40. Keep that in mind. What he has asked to determine is the value of k, not k dash. From the graph we can find what is the value of k dash. Use this relation, k dash is equal to k by 40, and find out what is the value of k later. So we obtained the time constant form. Next, moving ahead, let me go for step number 2. In step number 2, I should discuss the various factors. Discussion of factors. So first one is constant k. It is unknown. I should find what is the value of k. Moving for second term, it is 1 by s. 1 by s is what? 1 by s is pole at origin. That is one pole at origin, because the power of s is unity. One pole at origin. For one pole at origin, what is the contribution? It is the straight line of slope minus 20 dB per decade, intersecting 0 dB at 1 radians per second. Correct? This I already discussed with you in our previous problem and also in our first lecture of Bode plot. Next, moving for third one, we have simple pole. What is that simple pole? That is 1 by 1 plus 0.25 s. So for simple pole, what is the slope of the straight line? It is also minus 20 dB per decade, correct? So therefore, for simple pole, 1 by 1 plus 0.25 s, how much is time constant? Time period is 0.25 seconds. And how much is corner frequency? Corner frequency is 1 by t, which is nothing but 4 radians per second. It is also the straight line of slope minus 20 dB per decade for frequency greater than or equal to how much? 4 radians per second. For frequency greater than or equal to 4 radians per second. Move for fourth one. Again we have one more simple pole. What is that simple pole? 1 divided by 1 plus 0.1 s. 0.1 s. So how much is time period? It is 0.1 seconds. And how much is corner frequency? 1 by t. It is 10 radians per second. If you observe, the corner frequencies are in increasing order. This is corner frequency 0, 4, 10. They are in increasing order. Directly I can put it to the table as it is. Now what about this? This is also a straight line. The straight line, and what is its contribution? Minus 20 dB. The straight line of slope minus 20 decibels per decade for frequency greater than or equal to 10 radians per second. So we have discussed all the factors. Totally we have 4 factors. One is k, which is unknown to be computed. Then we have one pole at origin. Then we have 2 simple poles. I have discussed all of them. Next, moving ahead for step number 3. So in before moving for step number 3, I should draw resultant slope table, correct? Let me draw resultant slope table. Resultant slope table. If I go for resultant slope table, the first column should contain factors. Then we have frequency range. And then we have resultant slope. Resultant slope in decibels per decade. Decibels per decade. So first factor is k. We don't know what is its value. Next factor is one pole at origin, that is S inverse. Frequency is greater than 0 and it should be less than the next one. Next one is 4 radians per second. How much is the contribution? Minus 20 dB per decade. Since we don't have any value above that, the resultant will remains as it is. Next we have simple pole, that is 1 plus 0.25 s inverse, and its range will be 4 to 10, and its contribution will be minus 20, and previous value is minus 20, hence I will get the value as minus 40 dB per decade. Next, We have one more simple pole, that is 1 plus 0.1 S inverse. This pole frequency is 10 to infinity. So what is the contribution of simple pole? It is also minus 20. Earlier I had minus 40, contribution is minus 20. So the cumulative value is minus 60. So hope you followed how we are getting the resultant slope table. So this value is this and this value is this. Clear? So this completes our step number 2. Next, moving for step number 3, that is phase angle plot. If I move for phase angle plot in step number 3, step 3 is to compute phase angle. So using which I should calculate what is the phase crossover frequency. For this problem, phase crossover frequency is equal to gain crossover frequency, because is given the condition marginal stability. For marginal stability, phase crossover frequency must be equal to gain crossover frequency. Now let us find what is the phase angle by using the standard time constant form. Replace S by j omega in the standard time constant form of the given function. If I do that, I will get g of j omega h of j omega is equal to k dash, that is k dash plus 0j divided by, replace s by j omega of 1 plus 0.25 j omega into 1 plus 0.1 j omega. Right, now take the phase angle equation. So for constant it is 0, tan inverse of 0 by anything is 0, tan inverse of 0 is 0, leave it. Next, this is 1 by s. What is the angle contribution of one pole at origin? Minus 90 degree. This you people already know, or else you can write it as 1 by tan inverse of omega by 0. Real part is 0, imaginary part is omega. 1 divided by tan inverse of omega by 0, that is 1 by tan inverse of infinity. How much is 1 by tan inverse of infinity? It is 1 by 90 degree. How to write 1 by 90 degree? It is nothing but minus 90 degree. Next, these two are in denominators, therefore it is minus tan inverse of imaginary part is 0.25 omega, real part is 1, minus tan inverse of imaginary part is 0.1 omega divided by real part is 1. So I got the equation for phase angle. Now without plotting board plot, I can determine what is the phase crossover frequency. What do you mean by phase crossover frequency? The frequency at which the phase angle is minus 180 degrees is called phase crossover frequency. Using the definition of phase crossover frequency, first you find out what is the phase crossover frequency. That is, I already explained in our previous lecture. Let me explain once again here. It is phi value is already known, that is minus 180 I should get. So minus 180, we have minus 90 in the RHS, take it to LHS, it will become plus 90. Alpha is equal to, I left out with minus tan inverse, right? It is minus tan inverse of 0.25 into alpha x, close the bracket, minus shift tan inverse of 0.1 into alpha x, close the bracket, shift solve. You should press equal to, otherwise you will get the previous answer. The solution for previous problem is 6.32, that is stored in the memory. You press equal to, it will calculate and give you. So here also I am getting the answer as 6.32 only. So it is minus 180 plus 90, 0.1 omega and 0.25 omega. So if I solve, I am getting the same answer, 0.63245. So therefore The phase crossover frequency for this problem is also 6.324. So now I can build the phase angle table, that is values of omega, values of phi, values of omega, values of phi, values of omega, values of phi. So build the phase angle table. So I know the phase crossover frequency as 6.325 radians per second. So therefore I should have the values 6 and 7 because it is coming between 6 and 7. Next I will take 5, 3, 1. Here I will take 0.1, 0.2, 0.3, 0.5, and here I will take the values as 10, 20, 50 and 100. Now find the values, that is minus 90 minus tan inverse of 0.25 into 0.1 minus tan inverse of 0.1 into 0.1. So I'll get the angle as minus 92 degrees. Phase angle is in degrees, whereas omega is in radians per second. Keep that in mind. For 0.2, how much you are going to get? For 0.2 you will get minus 94 degrees. For 0.3 you are going to get minus 96 degrees. For 0.5 you are going to get minus 100 degrees. For 1 you are going to get minus 110 degrees. Like that you fill up the table. For 100 I got minus 262. So this completes the phase angle table. Now using the resultant slope table and phase angle table, I can plot magnitude as well as phase angle against the frequency in log scale, that is Bode plot. Come, let us move for step number 4, wherein which we are going to do Bode plot. Come, let us do that. Now moving ahead for step number 4 to plot Bode attenuation curve, we have the problem like this, for which we have just now determined the magnitude plot, that is resultant slope table, as well as phase angle plot table. Now if you observe, the maximum resultant slope I require is minus 60 decibels per decade, and we want to find the value of k for marginal stability. For marginal stability, people already know that I have mentioned that for marginal stability, omega phase crossover frequency must be equal to omega gain crossover frequency. This is the condition for marginal stability. Kindly make a note of it. Using that, let me determine what is the value of k. Come, let us plot the Bode attenuation curve. The semilog sheet you people already know. In our previous problem itself I clearly explained. Since maximum is minus 60, let me start the problem with plus 60. Correct? So positive values are used to generate negative slopes. So I'll start the problem with plus 60. Then 1 unit I will choose it as 20. So 60, 40, 20, 0 decibels, and then minus 20, and let me keep it at minus 40. Now for angle plot I will start with 90 degrees. Each unit I will take it as 30 degrees as usual, hence it will be minus 120 degree, minus 150 degree, and minus 180 degree, which is a reference for phase angle plot, then minus 210 degrees, then minus 240 degrees, and then minus 270 degrees. So I marked for magnitude plot till here, and then phase angle plot starting from minus 90 degree. Why I started at 60? Because maximum I require is minus 60 decibels per decade. As usual, generate the slope of minus 20, minus 40 and minus 60 lines by connecting the 0 dB at 1 radians per second. 0 dB at 1 radians per second. If you carefully observe, the ranges of frequency are from 0 to 4, 4 to 10, and from 10 to infinity. So as usual, no change is required. Mark from 0.1, 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and 10 to the power of 4. So this is frequency in radians per second. That is the x-axis, common for both magnitude and phase angle plot. Now take the reference as for magnitude plot. 0 decibels is the reference line. At 0 decibels, draw the line. At 0 decibels I mark, and also at minus 180 degree I want the reference, so mark at minus 180 degree. Done. I marked the references at 0 degree and minus 180 degree. Now to generate the slopes, as usual, at 1 radians per second, the decibels is 0, join all the slopes. Since I want negative slopes, join from positive values. If you want positive slopes, then join from negative values. Now I want negative slope, hence join from positive value. So join 0 dB at 1 radian per second from each of these 3 lines which I require. That is minus 20 generated, next is minus 40, done, and next is minus 60. Done. So these are what? These are slopes of minus 60 decibel per decade. This is minus 40 decibel per decade, and this is minus 20 decibel per decade. Done. Now if you observe, we don't know the value of k. K itself is unknown. I want to find the value of k. Hence there is no shift. That is 20 log 10k shift is not there for this problem. So therefore 0 line itself is the reference. So generate minus 20 slope. No need to take parallels and shift it to 20 log 10k, because k value itself is not known for us in this problem. So starting from the given obtained slope itself, I should extend minus 20 decibels per decade from 0 to 4 radians per second, correct? So where is 4 radians per second? This is 1, this is 2, 3 and 4. This is 4. So extend the line as it is from till 4 radians per second. This is 1, 2, 3 and 4 till here. Extend the line till here, 4 radians per second. To avoid confusion, let me leave some part not darkened so that you won't get confused. That is the line itself, what we generated for minus decibels per second itself is the starting line, because we don't have shift of 20 log 10k. If we have a shift of 20 log 10k, then we should draw a parallel line for this, such a way that it will shift to the 20 log 10k decibels at 1 radians per second, and that will become the starting point. From that line, for the given range of frequency, we should start the problem. But for this problem, k itself is not known. So therefore, whatever I obtained for minus 20 decibels per decade itself is the starting line. So for which I started the problem till 4 radians per second. Done. Next, the slope is minus 40 from 4 radians per second to 10 radians per second. So go for minus 40 slope. This is minus 40 slope. Draw parallel line for minus 40 slope from 4 radians per second. So draw parallel line from 4 radians per second to 10 radians per second. So this is 10 radians per second. So 4 to 10 you draw minus 40 slope. Then from 10 radians per second to infinity it is minus 60. So draw a line parallel to minus 60 from 10 radians per second to infinity. So draw a line parallel. If you use roller scale, it will become much more easier to draw parallel lines. So for minus 60 from the end of minus 40, that is at 10 radians per second, from there to infinity. So I'll draw it. Done. So this is what? Minus 20, this is minus 40, and this is minus 60 resultant slopes. Magnitude plot is over. Now if you ask me what is the gain crossover frequency, obviously it is 1 radians per second, because at 1 radians per second the magnitude plot is crossing 0 decibels line. That itself is a reference to generate the slopes of various lines which is required, correct? Since there is no shift, if there are no shift for all the problems, 1 radian per second will become the gain crossover frequency if we don't have any shifts, that is 20 log 10 k shift. Now move for phase angle plot. Coming for phase angle plot at 0.1 minus 92 degrees. At 0.1, so this is 0.1. At 0.1 it is minus 92 degrees, correct? Minus 92. Here itself I will mark nearly 90. 0.2 minus 94. This is 0.2. For 0.2 it is 94, but one line is 6 degrees, right? I think you have already watched my previous lecture. Hence, assuming that you people already watched my previous lecture, I am going bit fast. Next for point 3, point 1, point 2, point 3, how much is the angle? 96. Each subunit is 6 degrees, hence it is 96 will come here itself. This is 96. Then 100 for 0.5, 0.1, 2, 3, 4, 5. For 5 it is 100, 96, 102. So 100 will come here. Next 110 for 1. For 1 it is 110, that is 120 minus 6 is 114, minus 6 is 108. So between this I will get 110. Next for 3, 1, 2, 3. For 3 radians per second it is 144. For 3 it is minus 144, that is 150 minus 6. Here itself I will get 1, 2, 3. Next for 5 minus 168. For 5 168, 150, 156, 162, 168. Next for 6 177 minus 177. 5 for 6 177, almost here, and for 7 it is 185, and for 10 it is 203, 186, 192, 198, 204. So it will come here. Next for 20 minus 232. This is 10, this is 20. For 20, 232. It is 240 minus 6 is 234. 232 is half of that. Will come here. Next is 254. 254 is for 50. 10, 20, 30, 40, 50. For 50, it is 254. 240, 246, 252, 254. Each subunit is 6 degrees, that you know, right? Because for 5 divisions it is 30 degrees. 1 division is how much? 6 degrees, because 5 6 are 30. Next for 100 it is 262. For 100 it is 262. Now you draw smooth curve for this marking. Draw smooth curve. Join these points with smooth curve. Freehand sketch. Done. Now the phase angle plot is crossing minus 180 degree between 6 and 7. So between 6 and 7 we have the answer, but we already know what is the phase crossover frequency by using alpha x technique using calculator. It is 6.32 radians per second. So mark the phase crossover frequency. Phase crossover frequency is here. It is between 6 and 7. Mark it. And we know that for marginal stability, phase crossover frequency must be equal to gain crossover frequency. For marginal stability, the condition is phase crossover frequency must be equal to gain crossover frequency. Clear? So here we got omega phase crossover frequency as 6.32 radians per second. Now for marginal stability, we know that omega gc must be equal to omega pc. Omega pc 6.32. If omega gc must be equal to 6.32, this entire phase angle plot should move upward such a way that the phase angle plot crosses the 0 dB line at this point, that is 6.32 radians per second. For that we should shift the entire phase angle plot, correct? Like this. We should shift the entire phase angle plot. We should shift the entire phase angle plot like this. Then only I will get the gain crossover frequency as 6 radians per second. So if I get a shift like this, then only I will get, correct, the gain crossover frequency at. So this is the shift which I required, parallel to minus 20, minus 40, minus 60. If it shifts like this, then I would have got the gain crossover frequency as 6.32, correct? Now this shift is required for marginal stability. If this shift is attained, then gain crossover frequency will be equal to phase crossover frequency, correct? Now how much shift is required is what? Gain margin, correct? This is what? Gain margin, right? So that shift is nothing but gain margin. Find it out. A to B shift is required for marginal stability, correct? So what does it mean? For marginal stability, omega pc must be equal to omega gc, for which the magnitude plot must shift from A to B. The shift can be happen only by K, correct? 20 log 10K can give us this shift. This people already know. Hence, how much is the gain margin? How much is the gain margin I am going to get for this problem? That is, I have bit slight higher than minus 20 line. So how many divisions I'll get? 1, 2, 3, 4, 5.5 I can take. 5.5 divisions I can take. Each division is how much? Each division is 4 decibels. Each division is 4 decibels. So I have 5.5 divisions. So 5.5 into 4, which is nothing but 22 decibels. So hence this shift is how much? This shift is nothing but 22 decibels. The shift required is 22 decibels. The shift required is nothing but 22 decibels. Now what the problem we have? In the problem we have the standard form as k dash. The standard form itself is what? K dash divided by s of 1 plus 0.25s into 1 plus 0.1s. This is the standard form what I have, correct? In the standard time constant form. Hence 20 log 10 k dash must be equal to 22 decibels. Then only I will get this shift, right? The shift is nothing but what? 20 log 10k. 20 log 10k must be equal to 22 decibels. Then only I will get this shift. But what we have here is k dash in the question. So therefore, from the analysis it is clear that the shift can be achieved with 20 log 10 k dash is equal to how much? 22 decibels is the shift required. So if I solve 20 into log of alpha x is equal to 22, shift solve is equal to, if I solve I will get the answer as 12.589. so therefore k dash is how much? K dash is 12.58. Now what is the value of k dash? K dash is k by 40, hence the value of k can be determined. Substitute for k dash. K dash is k by 40, which is 12.58, hence the value of k is equal to 12.58 into 40, 12.58 into 40, which is 503.2, 503.2. so this is the value of k. So we have calculated the k for this problem for marginal stability as 503.2. Now let me fix and write the axis, scale, everything. So from here to here it is magnitude plot, and from here till here it is phase angle plot, correct? So this is phase angle in degrees, phase angle in degree. From here till here it is magnitude plot in decibels, magnitude in decibels, magnitude in decibels. Now what is the scale that I used? If I write the scale that I used for y-axis, for y-axis 1 unit is equal to 20 decibels for magnitude, and 1 unit is equal to 30 degrees for phase angle. For phase angle I used 1 unit as 30 degrees, for magnitude I used 1 unit as 20 decibels. Each subunit will become 4 decibels for magnitude, 6 degrees for phase angle plot, using which I solved the problem. The question given is that g of s into h of s is equal to, g of s into h of s is equal to k divided by s of s plus 4 into s plus 10. This was the problem given. So try to use roller scale to draw parallels. Like for 40 I drawn parallel, like this I drawn parallel for 40. Similarly for 60 I drawn parallel for minus 60, like this, by sliding the scale. To avoid error, make use of roller scale. If you use roller scale, you can avoid errors. So this is what the answer I got. K is equal to 503.2. This is for magnitude and this is for phase angle. That is the scale for y-axis. This is the complete solution for problem number 2, wherein which by using marginal stability condition we determined the value of k. That's all from this lecture. Thank you all.